Here in 11.3, we'll be looking at the integral test and using it to estimate the sum of a series. So to get the basic idea what we're doing with an integral test, let's think about how the sum of a series would compare with an improper integral. So for instance here, if we're looking at the sum of the series 1 over n squared, we can imagine that graphically we're summing up these rectangles, right? Each of these rectangles has an area that's equal to a term of the series. So we're summing up all of these rectangles, and if we compare that with the area under the curve y equals 1 over x squared, we can see that the integral from 1 to infinity would correspond to the area under the curve. And in this case, if we compare them, it looks like, because well, actually not including this first rectangle, but starting with the second rectangles, so starting with the second one here, it looks like those would be smaller. So here I can actually just, to make it correct there, we can add the 1 there. So comparing them, we can see that the sum of the series 1 over n squared is less than or equal to 1 plus the integral from 1 to infinity of 1 over x squared. And we actually know that this value converges, right? We know that the integral from 1 to infinity of 1 over x squared converges. Since we know integral of from 1 to infinity of 1 over x squared, we can evaluate, right? It's the limit as t goes to infinity, integral from 1 to t, x to the negative 2. Integrating that, we'll have negative 1 over x evaluated from 1 to t. So it would be negative 1 over t minus negative 1, so plus 1. And as t goes to infinity, this goes to 0 plus 1. So since we know the integral from 1 to infinity here converges to 1, we know that the sum of the series 1 over n squared must be less than or equal to 2. So what this shows is that in fact this series must converge. Let's look at it in a different way. Let's consider the series 1 over the square root of n. And again, here we can visualize this graphically with a bunch of rectangles here whose area are equal to each term of the series. And again, if I compare this with the area under the curve from 1 to infinity, notice that the way we've drawn the rectangles in this case is a little bit different now, because now I've drawn them so that they are above the curve. So we see that the area under the curve is going to be smaller than the sum of these rectangles. And therefore the sum of the series would be greater than or equal to the integral from 1 to infinity of 1 over the square root of x. And again, this is an integral that we can evaluate. We've done this one. We know that this is the limit as t goes to infinity, integral from 1 to t, x to the negative 1/2 power, which evaluates to 2x to the positive 1/2 power. So taking the limit as t goes to infinity, 2 times the square root of t minus 2, we see as t goes to infinity, this goes to infinity. Therefore, the sum of the series here must also be something greater than infinity, greater than something that goes to infinity. Therefore, it must also be divergent. Right, so here the integral diverges. So therefore we can say that since this is bigger than something that diverges, it must also diverge. Essentially, it's greater than or equal to infinity. Implies that the series must also diverge. Now, let's put this into a more formal test. And what the integral test says is that suppose I have a continuous positive decreasing function on the interval from 1 to infinity. So like we saw in the last few examples, right? We're looking at some function that's decreasing and going to the right, or decreasing as it goes to the right. So we're going to then suppose here that our series has terms that are given by points on that curve. Then the series is convergent if and only if the improper integral from 1 to infinity of f of x dx is convergent. What this really is saying is that if the integral is convergent, then the series is convergent, or if the integral is divergent, then the series is divergent. So essentially, whichever the however the improper integral behaves determines how the series behaves. Okay. But notice that, like what we saw in the previous example, that in general the integral, so this is an important note, the integral is usually not equal to the sum of the series. They're different, but they can be compared in a useful way here. In general, the sum of the series is different than the improper integral. So when we evaluate the integral, we're not actually getting the sum of the series. But if the integral has a value, all it tells us is that the series does converge. It doesn't necessarily tell us what the value of the sum is, but it tells us it does converge. And so we'll see in a moment that we can use the integral to help us estimate or approximate the sum of the series. Let's try using the integral test to help us evaluate or help us to show whether this series here converges. So we're looking at the series from n equals 1 to infinity of 1 over n squared plus 1. So what we want to do is compare with the integral from 1 to infinity of 1 over x squared plus 1. Well, first of all, let's think about the conditions of the integral test. First, we have to verify that this function is positive, continuous, and decreasing. So remember, that's one of the conditions for the integral test. So that it has to be positive, continuous, and decreasing on the interval from 1 to infinity. So let's just quickly verify that that's the case here. So clearly it's positive. 1 over x squared plus 1 will always be a positive value, regardless of, for any value of x, right? So it's positive. It's clearly continuous because notice that you'll never get a value of 0 in the denominator, so there's no points of discontinuity. And maybe the one thing that we have to check is that it's decreasing. And in this case, you can clearly see that it will be decreasing on the interval from 1 to infinity because, well, one way you can look at the decreasing part is you can take the derivative. And in this case, if I take the derivative, I would get negative 2x over x squared plus 1 squared. You can see that just by doing the derivative here. You would get negative 2x over x squared plus 1. So notice that this is going to be less than 0 for values of x that are greater than or equal to 1. So that shows that last part there, that it's decreasing. Okay, so now that we know it satisfies those conditions of the integral test, let's just take the integral from 1 to infinity of 1 over x squared plus 1. And in this case, we know that the integral here of 1 over x squared plus 1 is tan inverse. So I'll write the integral from 1 to t will be tan inverse of x. And then we'll evaluate the limit here. As t goes to infinity of tan inverse of t minus tan inverse of 1. As t goes to infinity, remember that tangent inverse will approach pi over 2. Tangent inverse of 1 is pi over 4. And then subtracting the values, we get pi over 4. So that tells us that because here the improper integral converges, we know that the series, the corresponding series, must also converge. And in this case, using the integral test.